everyone, welcome you all in our free foundation physics course. I'm very happy to welcome you all. So in this free foundation physics course, I have almost covered all the topics which you might be requiring for your physics competitive exams. We are almost towards the end of our free sessions. So 2 to 3 sessions are remaining, and we will be completing our foundation physics, and then we will be actually starting our syllabus. So if you want that your learning keeps on going, your learning does not stop. So purchase the course today itself. You can buy our courses on either on app or website. Okay, the courses are designed in such a way that all the information, all the content, all the resources that a student might need is available. You don't have to purchase or buy or go or look for any other thing. Once you purchase the course, everything, each and everything that you might be needing is there. Also, the main thing about the course is made very affordable. Our courses are most affordable, and being able to qualify all the exams myself, I have designed the course in such a way that you can easily manage the course with your BSc education or your MSc education. And you can get a very good rank by putting 3 to 4 hours of hard work every day. So that is the main purpose behind the designing of those courses. Okay, so let's begin with today's session. Today I'm starting rigid body dynamics. I will be covering this topic in 2 days. One today and another lecture will be uploaded tomorrow. In today's lecture, I will be discussing about moment of inertia, and tomorrow I will be discussing about angular momentum, torque, equations of motion, and so on. Okay, so let's see what is moment of inertia. Inertia word we first heard when we studied Newton's third law or Newton's first law. So when we studied Newton's first law, the law says that a body which is at rest wants to remain at rest, and the body which is moving with uniform velocity wants to keep moving with the uniform velocity. So body wants to maintain its state of rest or the state of motion. That property due to which body likes to maintain its state of rest or motion is known as inertia. But that was about the linear motion. Body wants to be either in linear motion or body wants to be at rest if it is at rest. But what about rotation? So whenever we talk about the rotation, the term inertia becomes the moment of inertia. So the inertia is a property due to which body do not want to change its state. Either it wants to remain at rest or it wants to remain in the motion. But what about the rotation? When we try to rotate the body, there is some inertia in a body. Body do not want to get rotated. And if body is already rotating, then body does not want to stop. So this property is known as moment of inertia. How do we calculate moment of inertia? The simple formula for moment of inertia is summation mi/ri square. Let me open this formula up for you. Let's say there are many masses, m1, m2, m3, m4, m5. So there are many masses in a body, and all of them will be rotating around the axis. So this is your axis around which your body is rotating. So what will be the moment of inertia of such a motion? So it will be mi means mass of first body multiplied by r1 square, but is an r1. R1 is a distance, perpendicular distance of this mass from the axis. Similarly, plus m2 r2 square, but is r2. R2 is a perpendicular distance of mass 2 from the axis. So this is how you calculate the moment of inertia if you have a discrete system. Discrete system, you understand that masses are placed separately. It is not a continuous body, it is a discrete body, just like we did in the center of mass. Okay, so there are some very good points here. Actually, I depends upon the axis. So let's say I have a body. Let me take one body. So let's say there is a sphere, or let's say there is a square body, and 4 masses are placed on the 4 edges. So it is a discrete system. Yes, there are 4 masses discretely placed on the 4 edges. Now the moment of inertia is not fixed. I cannot say that moment of inertia of this body is I. I have to define the axis. I can say that, okay, moment of inertia about this axis, if the rotation happens about this axis, then the moment of inertia is I. But what about the moment of inertia about the axis which is passing through the center and it is perpendicular to the square? So let's say there is a axis which is passing through the center and it is perpendicular to the surface. Then the moment of inertia about that axis will be different. So whenever we define moment of inertia, we do not define moment of inertia for a body. We define a moment of inertia for a body about fixed axis, about some axis. So both axis and body are needed to define a moment of inertia. For the same body, moment of inertia can be different around different axes. Okay, great. Next part is moment of inertia depends upon the mass of the body. Whatever is the mass of your body, your moment of inertia will always depend directly on it. So if your mass is more, the inertia will be more. And if the mass is less, inertia will be less. That is a known fact in the physics. Then the next part is the moment of inertia depends upon how far is your mass from the axis. Let's say I keep a body close to the axis, then the moment of inertia will be less. But if I keep this mass away from the axis, then the moment of inertia will be more. So this is also one of the very major point that you should have in mind whenever you are thinking about inertia or whenever you are visualizing the problem. These facts should come to your mind. Okay. Now let's do this one example in order to solve the problem. So the example in front of you is that there are four masses are placed on the edges of the square. So mass m are placed on the edges of the square, and what is going on here is you want to find the moment of inertia. So around this axis is a diagonal axis. So let's apply the formula. So the formula says summation of mi ri square. So let's call this mass number 1. So I will say m1 into r1 square plus, let's call this 2, m2 into r2 square plus m3 into r3 square plus m4 into r4 square. Let's call this 3 and let's call this 4. So what will be the distance of m from axis? It is 0 because it is sitting on the axis. So if something is sitting on the axis, then the distance of that mass from the axis is 0. So first term will get 0. What is the perpendicular distance of mass 2 from the axis? So this is a perpendicular distance of mass 2 from axis. And you should know that this distance is known as a by root 2. It's a very common fact. You can use the trigonometry to prove this. So m2 is m and r is a by root 2 square. Similarly, what about r3? R3 is sitting on the axis, so it means 0. And what about r4? The same distance, a by root 2. It means a by root 2 whole square. So your total answer will be m a square by 2 plus m a square by 2, which is m a square. So this is the moment of inertia about axis 1, which is diagonal. Now what about the moment of inertia about an axis which is passing through the center? So let's say this is your square and there is one axis which is passing through the center and there are four masses, m, m, m and m. Fine. What will be the moment of inertia around this axis? Now you can clearly see all the masses are at distance a by root 2 away. All the masses are a by root 2 distance away. So I can simply write 4 times m into a by root 2 square, which will be 4m a square by 2, or you can say 2m a square. Okay, so this will be the moment of inertia about given axis, which is perpendicular to the surface of the square. So all the masses are at distance a by root 2. So I found the moment of inertia due to one mass and I just multiplied it with the 4 because there are 4 masses. I hope that you understood this example. This is one of the simplest example to understand how the moment of inertia formula works. Okay, let's come to the next part. What if the bodies are continuous? Just like in center of mass, we did first discrete masses and then we studied the continuous masses. Similarly, in the case of moment of inertia, we will do the same thing. So if the bodies are continuous, then the summation is replaced by integration. Okay, r square remains r square and m becomes dm, small mass dm. So this is a formula that your moment of inertia is r square dm integration. Okay, so this will give you the moment of inertia. Okay, Now, before we go on deriving the things or before we start calculating the things, I just want to ask you one question based on your physical intuition. That let's say you have one ring. This ring has a radius of mass m, and this ring has a radius r and mass m. Similarly, there is one disk. Now, disk also has a radius r and a mass m. Without using the formulas, without going into the formulas, what do you think? Which will have more moment of inertia, ring or disk? So I will pause for 10 seconds. You think about it. Will the ring has a more moment of inertia or will the disk has the more moment of inertia? So in order to answer this question, you should think about this term. This line, farther the mass is from the axis, more will be the moment of inertia. So just you can pause the video and try to think about it. I will give you the answer. So if you want to think about it, pause the video. But the answer to this question is the ring will have the more moment of inertia. Why? Because here you clearly see all the mass is away from the axis. So this is an axis. So what is an axis? Axis is something passing through the middle center of the ring or the disk, and it is perpendicular to the ring or the disk. So you can clearly see the entire mass is away from the ring, from the axis. But in this case, some mass is close to the axis, some mass is away. So mass is not entire mass is away. Some mass is even close, some mass is away. So this will definitely has the less moment of inertia, and this will definitely have the more moment of inertia, because if the mass is away from the axis, the moment of inertia is more. And in this case, the entire mass is away from the axis, so the moment of inertia surely will be more. And in this case, some mass is closer to the axis also, so it means that moment of inertia will be less. Now let's prove this fact. Let's try to prove this fact using the actual approach, actual formulas. So first we will derive the moment of inertia due to ring. Why I am deriving all this? Why can't I give you the direct formulas? The importance is that in questions, they will never ask you direct form. They will give you some mass density, some body, and the answer will lie in the derivation itself. So you have to derive the moment of inertia for that specific kind of object or that specific kind of mass density. So you should be aware that what are the steps that are being used in the derivation, so that you can use the derivation, you can modify the derivation for the problem which is given to you. Okay. So let's say there is a ring, and that ring has a total mass of capital M, and that ring has a radius of capital R. Now, if I want to find the moment of inertia, the basic requirement is I have to use a formula which is given by R square dm. It means I have to assume some small mass dm. So let's do that. So let's consider a small mass having a length dl on the ring, and this length dl will have the mass dm. Now I will just want to give you the rules to find dm. Whenever you want to find dm, which means the small mass, you use the formula lambda dl. If it is 1D body, you use the formula sigma dA if it is 2-dimensional body, and you use the formula rho dV if it is 3D body. What is lambda? Lambda is mass per unit length. Sigma is mass per unit area, and the rho is mass per unit volume. So you should remember this fact, that how do we find the small mass d? Because in the problems, many times this thing will be given to you. Lambda will be given to you, and you will be asked to find the moment of inertia for any body. Or sometimes sigma will be given to you, or sometimes rho will be given to you. So always remember, you should be well aware about these derivations. Okay, so remember this method or rule to find the dm. Okay, so let's find this dm for ourselves. So we have assumed this small length dl. What will be this small mass? What will be the mass of this small element? So that will be dm. Dm, as I mentioned, is lambda dl. And what is lambda? Lambda is mass per unit length. So what is the total mass of the ring? M. And what is the total length of the ring? 2 pi r. So your lambda is m by 2 pi r. So I just put the value of lambda here, and I will get this m dl divided by 2 pi r. Now let's use the formula for moment of inertia, r square dm. R is fixed. So you can clearly see wherever I go, for all the masses, small masses, the r will be fixed, which is capital R. So I will put r square as capital R square. I will put the value of dm, and then I can take everything outside because r is fixed. So this r and this r can cancel each other. So everything is fixed. So it will come out of the integral. And only thing you have to integrate is dl. And your length is going from 0 to 2 pi r. So once you do that integration, so dl integration is L. And if you put the limits, you will get 2 pi r. So what you will get is you will get a formula moment of inertia as mr square. So the moment of inertia for ring is given by mr square. Very important. Very, very important. Extremely important, I would say. The formula is used many times directly or indirectly in the questions. Okay. Now let's talk about the disk. How do we find the moment of inertia for a disk? Again, the same principles or the same rules applies. So now you will assume a small ring. You will not assume a small mass. You will assume a small ring. So if you assume a small ring, then this ring has a radius of r, and this ring has a thickness of dr. Very nice. So what will be the small mass of this ring? What will be the small mass of this ring? So now it is a two-dimensional body, right? So if it is a two-dimensional body, then dm will be sigma d. What is sigma? Sigma is mass per unit area. So the total mass of a body is m, and the total area of the body is pi r square. So sigma is m by pi r square. And what is dA? What will be the area of this small ring? It will be 2 pi r into dr. Okay, so you got your dm. Just put the value of dm in your moment of inertia, r square dm. So I put the value of r square dm. So I can take this m outside, 2 outside, small capital R square outside, and I just have to do an integration of r cube dr, and your radius is going from 0 to capital R. So if you do this integration, you will get a formula of mr square by 2. So the in moment of inertia of this case, mr square by 2. Very nice. Fantastic. Okay. So your moment of inertia disk is mr square by 2, and the moment of inertia of ring was mr square. So you can clearly see the moment of inertia of ring is greater than moment of inertia of disk. And this is what we predicted. We also predicted the same thing, that ring will have the more moment of inertia. And in fact, this is a true fact. Okay. So I hope that you understood the derivations. In case you have any doubt, please feel free to contact me either in comments or in Telegram channel, wherever you like to. You can contact me and we can have a good discussion on this. Okay. Now let's come to the next part. Rod. The object number 3, which I want to cover. So let's find a moment of inertia of rod. So there is a rod which has a total mass m and the length l, and you want to find a moment of inertia around an axis which is passing through the center of the ring. Oh, sorry, center of the rod. Again, the same step. Consider a small mass dm having a length of dx. Okay, so what will be the small mass of this this element? Again, it is a one-dimensional body, so the rule will remain same. Dm will be lambda dx. What is lambda? Lambda is mass per unit length. So total mass is m and the total length is l. So mass per unit length will be m by l. So I will just put the value of lambda as m by l into dl. Simple. Not I can put here dx. Okay. And then the moment of inertia formula is r square dm. So here instead of r, you can take x. You can just, it's just a naming. So I can, instead of naming r, I can name it as x because it's a one-dimensional body. So r is replaced by x. So x square dm. So I put the value of dm. So I get x square dx, and here I get an integration of from minus L by 2 to L by 2. So here I did a very interesting step. I just want to mention this so that it will also help you in the future classes. So you see, I replaced my integration from minus L by 2 to L by 2 to 0 to L by 2. And I just put 2 in front. How I can do this? So there is a very simple rule. If you have an integration of any function from minus a to a, you can write it as 2 times from integration from 0 to a. In which case you can do this when the function fx is even function. Whenever your function is an even function, you can do this. If your limits are from minus a to a, you can write it as 0 to a and just multiply it with 2. And when you can do this, when fx is an even function. What are even functions? Even functions are like x square, x4, cos x, all these are even functions. What is even function? Even function is a function whose value at minus x and x is same. So you can clearly see if your function is x squared, then the value at minus 3 is also 9 and the value of 3 is also 9. So if your value at minus and plus is same, then those functions are known as even functions. And in that case, you can use this property. So what I did was I replaced my integration of minus L by 2 to L by 2 into 0 to L by 2 and I just multiplied it with the 2. Now what will be the integration of x square? It will be x cubed by 3. And if I just put the values, I will get a moment of inertia as ml square by 12. This is also very important formula that you should always remember. Okay, moving on. Now I want to discuss two very important theorems in moment of inertia. One of them is parallel theorem and one of them is perpendicular axis theorem. What is parallel axis theorem? So let's assume there is one body and there is an axis passing through the center of mass. So this is center of mass and there is one axis which is passing through center of mass. And there is one more axis which is passing through some random point P. And this random point P is at distance r away from the center of mass. So if you know the moment of inertia around your axis which is passing through center of mass and you want to find the inertia through a random axis, then the formula is moment of inertia through axis I will be equals to IC plus mr square. What is IC? IC is a moment of inertia about an axis passing through center of mass. And what is I? I is a moment of inertia about an axis which is parallel. This axis is parallel to the axis which is passing through center of mass. So this is a rule. This is a very basic fundamental rule that you can apply. Okay. Similarly, there is a perpendicular axis theorem. Let's say you have a body in which there are three axes which are perpendicular to each other. Let's call one axis as x-axis, another as y-axis, and the third as z-axis. Now let's say you know the moment of inertia around two axes in a plane. Let's say you know ix and you know iy, and you want to know iz. Then iz will be nothing but the summation of ix plus iz. So if you add the moment of inertia around x and y, you will get a moment of inertia around z. That is a very basic principle. Okay. Now let's try to see this in a ring. So what do I want to know in the ring? So in ring, I have already calculated that moment of inertia around z-axis means axis which is passing through center and perpendicular is mr square. So the moment of inertia around ring will be around z-axis will be mr square. What I want to know is what is a moment of inertia around x-axis and what is a moment of inertia around y-axis. Now from the symmetry, the body is symmetrical. You can replace x and y and nothing will change. It means the moment of inertia around x and y should be same because of the symmetry of the system. So we can assume that ix and iy are same. Then we will use a perpendicular axis theorem and we will say ix plus iy equals to iz. Since ix and iy are same, so I can write it as 2ix and it will be equals to iz, which is mr square. So my ix will be mr square by 2. Same will be my iy because iy and ix will both be same. So this is the application of perpendicular axis theorem. So we knew the moment of inertia around z and we calculated the moment of inertia around y and x. Very nice. Let's come to the next point. Let's say now we know iy. Iy we calculated, right? Now I don't want to know about the moment of inertia around this axis, but I want to know the moment of inertia about this axis, the tangent axis. This is known as tangent axis. So tangent axis. So what will be the moment of inertia around tangent axis? We will use the parallel axis theorem. What is parallel axis theorem? So this axis is passing through center of mass, right? And we know the moment of inertia around this, which is mr square by 2. And then we will add mr square to find a moment of inertia around this axis. We added mr square. So what will be our total answer? It will be 3 by 2 mr square. So the moment of inertia around this axis will be 3 by 2 mr square. Fine. So this was an application of parallel axis theorem. Okay. Now, this is a table that you should be remember. In this table, the moment of inertia of some bodies are given to you. For example, ring we already discussed. Disk we already discussed. Similarly, solid cylinder. You should be knowing the moment of inertia around solid cylinder. It is same as disk. So it is also mr square by 2. Similarly, rectangular plate. So if a rectangular plate is given to you, how do you find the moment of inertia? So it is m by 12. So it is m by 12. Okay. So it is m by 12 a square plus b square. So here it should be divided. Okay. So there is one by missing here. Similarly, for rod, it is ml square by 12. For solid sphere, it is 2 by 5 mr square. For hollow sphere, it is 2 by 3 mr square. For hollow cylinder, it is mr square about the axis. And for triangular lamina, it is mh square by 6. So you should be remembering these formulas, very important. You should make a list of them, and these will be used many times in the questions directly. Especially, I would recommend you to remember the formula for solid sphere and hollow sphere. Very important. It comes almost every year in any exam. There is some hint always regarding to this two bodies. Okay. Okay. Now, in the end, I want to discuss one question. I will not be discussing too many questions in this class, because after our rotational motion is done, I am going to take a live session in which I will be discussing many questions. So just to complete, I will be discussing one tough problem. This is a tough problem. This is also this kind of problem came in TIFR exam. So I always take TIFR exam as my upper edge, because whatever is asked in TIFR and CSIR net. So whatever is asked in TIFR and CSIR net part C, that is one of the toughest things you can think about in physics. Okay. Not every question, but many questions. So not every question of TIFR is very hard, but there are many questions which are hard. But the best part about TIFR is the question repeats itself. So once you cover all the PYQs in a good manner, that will be covered in our course, then you will see that those same concepts are being repeated. If you have solved our calculus PYQ assignment, PYQs of TIFR, which I provided you along with the detailed solution, then you realize that there was one formula for the series expansion that were being used in 3 to 4 problems. Similarly, in collisions, the questions I discussed, once you know that concept, then you can see that, okay, the same concept is being repeated again and again every year in the questions. So that is a beauty of TIFR exam. It is tough, but the concepts repeat itself. They just want to see that have you made an enough attempt to make sure that you cover the topics which are being asked in the previous exams or not. Because mostly the guidance for TIFR is not available. And that is very sad part, because those questions are really good. And that actually makes you very good physics student. Okay. So now let's come to our problem. The problem is there is a circular disc. So there is a disc and you cut the part from this disc, and the part you have cut has a radius of r. The remaining part, this remaining part has a mass capital M. The whatever remaining is there, the mass, it has a mass of capital M. The first question which is asked to you is, what is the mass of the full disc? So I will repeat it myself, that the remaining part, whatever is the remaining part, that has a mass M. Now let's assume nothing was cut out, everything was there. Then what will be the mass? And the second thing you want to tell is, what is the mass of that cutout part? What is this mass of cutout part? Once you find these two informations, then they are asking what is the moment of inertia of the final body. So these are the three things that we want to find. So let's do it. So the mass of the remaining part is capital M. What about sigma? Sigma is mass per unit area. So mass per unit area is mass divided by remaining area. What is the remaining area? It is total area minus area cut out. So what is your total area? Total area is pi r square. What is your cutout area? Pi r square by 4. Because if you put r as r by 2, you will get r square by 4. So what is your sigma? Sigma is 4m by 3 pi r square. Now we can calculate the moment of inertia full disk. Again, we will be using the same formula, sigma A. Whenever two bodies are there, mass is given by sigma into A. And if you are talking about small mass, then it will be given as sigma into small d. But if you are talking about the full mass, then it will be mass into sigma into total A. So sigma you have already calculated. It is 4m by 3 pi r square. What about this A? What about the area of the full disk? Area of the full disk will be pi r square. So if you just cancel these things, you will get 4 by 3 m. So if the mass of your remaining part is m, then the mass of the full disk will be 4 by 3 m, which makes sense because 4 by 3 m is greater than m, which is true. If you do not cut out anything, then obviously your mass will be more, and it is coming out to be more. Now, what about the mass which you have cut? What about the mass which you have cut? So the same rule applies here. Sigma A. So sigma you have calculated. What about A? A is pi r square. But what is radius now? R by 2 square. So if I put that, I will get m by 3, which makes sense. So the full disk has a mass of 4m by 3, and the disk which you have cut has a mass of m by 3. So that makes sense. So if you, from the full disk, if you subtract the mass of the cutout portion, then you are getting m, which is exactly the thing which we have, right? So from the full disk has a mass of 4m by 3. If you cut out the mass of this small disk, which is m by 3, then you get the mass of the remaining part, which is m, which is true. The remaining part mass is given to us is m. Fine. Now let's come to the next part. The next part says, what is the moment of inertia of your body? So if you remember the center of mass problem, how we solved the cutout portion mass there. So what we did is we first find the moment of inertia of entire system, entire disk. So let's do that. The moment of inertia of full disk will be mr square by 2. And what is the mass of full disk? Mass of full disk is 4 by 3 times m. Okay, I can write here mf. Mf means mass of full disk. Okay, so the mass of full disk is 4 by 3 times m, r square by 2. You will get an answer of 2 by 3 m r square. Okay, so the moment of inertia which you have calculated is around which axis? It is around the axis which is perpendicular to your disk and passing through the O, right? You know that the formula mr square by 2. It is the formula for a axis passing through the center of the disk and perpendicular to the disk. Very nice. Now let's come to the second part. Now let's find the moment of inertia of the cut part. So mass we have already calculated m by 3. What will be the moment of inertia of the cut part? It will be mr square by 2. Okay, again mr square by 2. What is the mass of the cutout portion? M by 3. What is the radius of the small part? It is r by 2. So r square will be r square by 4. And you will get mr square by 24. But what is this moment of inertia is about which axis? It is around this O dash axis, right? The axis which is passing through the center of the small disk. But you want moment of inertia around, so this moment of inertia is around O dash. So the axis which is passing through O dash, but you want moment of inertia about an axis which is passing through O. So what I will do, I will just simply add mr square. So I will just simply add mr square. So what is my moment of inertia around O axis? My already known moment of inertia, which is mr square by 4, and I will add mr square. What is a mass? M by 3. And what is a radius distance? So this distance between O and O dash is r by 2. So if I put r as r by 2, I get m by 3 r square r by 2 whole square. I will get an answer of mr square by 8. So what do I have? What have I calculated? So let me just briefly tell you that. So I have one disk, and I know that the moment of inertia of entire disk, is coming out to be 2 by 3 mr square. And the moment of inertia of a cutout portion around this axis is coming out to be mr square by 8. So what I will do, I will subtract the moment of inertia of cutout portion from the moment of inertia of total. So I will do the whatever is my total moment of inertia, I will subtract the moment of inertia of my cutout portion from that part, and I will get my final answer as 13/24 mr square. So what is the logic that I use? So first thing I did is find moment of inertia of full body about center axis O dash, sorry, O. Then what I did, find moment of inertia of cutout portion about axis O dash. Then I find moment of inertia of cutout portion about O. And now I have this I full around O and I have I cutout about O. Then the final moment of inertia is I full around O minus I full around, sorry, I cutout around O. So this will be my final answer. So this is the exactly the same thing I did. I full around O minus I cut out around O. So if I do this, my final answer comes out to be 13/24 mr square. So this is one of the typical problems, because in this problem, students miss out many steps. For example, they do not change the axis. They just simply subtract. So first, once you find the moment of inertia around O dash, you have to make sure that you replace it with the moment of inertia around O. So there are many steps involved. This is one of the toughest problem, which can be asked in terms of, the same thing can be asked to you in terms of spheres also. Here the example was for disk, but it can also be asked to you for spheres. Okay, so keep in mind that that can also be one of the question.